At the core of all industrial automation is a profound physical disconnect. The microcontrollers processing the logic operate on fractions of a volt, but the factory floor requires hundreds, sometimes thousands of pounds of sheer physical force. The hardware layer that bridges this gap, translating digital instructions into massive mechanical output, is the actuator. This slide outlines the hardware options available to engineers. We categorize them into three main domains: electrical, hydraulic, and pneumatic. While hydraulic systems are deployed for extreme raw force, and pneumatic systems for simple, high-speed applications, electrical actuators dominate modern precision engineering. They work entirely by modulating electromagnetic fields. When current flows through a conductor inside a magnetic field, it generates a strict, predictable push or pull, converting electrical energy directly into mechanical movement. This diagram shows the macro architecture of that translation. A low-voltage control signal from a microcontroller enters the motor driver, which amplifies and modulates the power. That current is then fed into the actuator, which physically executes the mechanical output. Designing a system capable of sub-millimeter precision requires understanding exactly how engineers manipulate this specific electromagnetic sequence to control physical reality. The most foundational application of this principle is the solenoid. This cross-section shows the internal geometry. Passing current through the stationary coil induces a strong magnetic field, pulling the metal plunger inward. When the current stops, the field collapses, and a mechanical spring forces the plunger back to its resting state. This basic linear push and pull is highly effective when deployed for rapid, specific industrial tasks. This diagram shows a primary use case, the automated fluid control valve. On the left, the unpowered valve is closed. Energizing the coil on the right lifts the plunger. As the green arrows demonstrate, this clears the path, allowing fluid to flow. The inherent limitation here is the absolute lack of variance. A standard solenoid is entirely binary. It can only hold a 0% or 100% engagement state. While perfect for managing fluid lines, binary action cannot execute tasks requiring proportional positioning or variable speeds. For that control, the system requires continuous rotary motors. The rotary DC motor solves the binary limitation by generating continuous, uninterrupted electromagnetic torque. As long as the electrical current is continuously applied, this rotational force quickly builds and maintains a massive amount of industrial momentum. This introduces a mechanical dilemma. The continuous force generated is rotational, yet automated systems like CNC machines and robotic arms strictly require straight-line, linear movement. This diagram illustrates the primary solution: coupling the rotary motor to a lead screw. The motor's continuous torque passes through the gearbox, spinning the lead screw. Because the drive nut is threaded onto that screw, the rotation forces the nut to travel linearly. For systems requiring tighter tolerances and reduced friction, engineers upgrade this mechanism to a ball screw. This cutaway reveals the internal complexity of a high-end ball screw system coupled to a synchronous motor. The critical physics trick here is the threading itself. The physical pitch of the screw acts as a massive mechanical gear reduction. It mathematically trades the rapid rotational speed of the motor shaft for heavily multiplied linear force pushing against the drive nut. This precise mechanical translation is what allows standard electric motors to push multi-ton industrial loads with sub-millimeter linear resolution. However, translating rotation into linear force only works if the system can perfectly control the exact angle of the motor's initial rotation. This requirement introduces the stepper motor, an architecture that purposefully sacrifices smooth, continuous motion to divide a rotation into distinct, measurable physical steps. This diagram shows the internal electromagnetic mechanism. The system fires stator coils in sequence to pull the central rotor into alignment. By shifting the field phase from A coils to B coils, the magnetic field rotates, dragging the rotor exactly one step clockwise. This physical sequence of coil excitation connects directly to the digital ones and zeros produced by a microcontroller. These logic truth tables map the digital states to the physical coil pulses. The full step table on the left provides high torque, but interleaving the signals in the half-step sequence on the right mathematically doubles the positional resolution of the rotor. An engineer's ability to sequence these steps depends heavily on the motor's internal wiring configuration. These schematics detail the winding setups. Whether the motor uses 4, 5, 6, or 8 wires dictates the current routing, requiring the engineer to select a matching driver circuit. This entire stepper architecture is defined as an open-loop system. The microcontroller fires the digital sequence and blindly assumes the motor executed the physical step. While steppers offer mathematically predictable precision, their open-loop nature means if physical resistance stalls the motor, the system never registers the error, creating a dangerous vulnerability. The engineering solution to that open-loop vulnerability is continuous real-time error correction. That requirement introduces the servo motor architecture, the ultimate closed-loop system. This block diagram isolates the logic of a closed-loop system. The physical output is constantly monitored and compared against the target command. The feedback loop routes sensor data back to the PID controller, calculating the exact error margin between the actual position and the requested position. This abstract control loop must be physically built directly into the housing of the servo motor. This schematic identifies those internal components: a high-speed motor, a gear train, and a potentiometer acting as the sensor. The potentiometer rotates with the output shaft. Its changing electrical resistance creates a varying voltage, representing the absolute mechanical angle, which is fed back into the comparator. To dictate the target angle to that comparator, the digital microcontroller sends a signal using pulse width modulation, or PWM. This timing diagram illustrates the communication. The logic is read from the exact duration of the high pulse in milliseconds. A 1.5 millisecond pulse holds dead center. Shifting the duration to 1.0 or 2.0 milliseconds sweeps the motor to its extremes. Because closed-loop servos actively hunt for a zero-error state, they will violently fight against any physical disturbance that pushes them out of position. This self-correcting rigidity establishes them as the standard for dynamic robotics. To master automation, you must recognize how all of these isolated concepts integrate into a single industrial application. This diagram shows the complete physical anatomy of an automated control valve. This single machine utilizes every layer of the stack we've analyzed, routing control signals through motor torque and gear reduction to manipulate a heavy physical pipe process. Overlaying the theoretical logic stack onto this hardware reveals the strict sequence of operation. Microcontrollers generate precision logic via PWM or step tables. H-bridges regulate high current. Motors generate electromagnetic torque, and mechanical screws apply massive physical force to the valve. Whether a system requires the binary speed of a solenoid, the discrete nath of a stepper motor, or the self-correcting feedback of a servo, electrical actuators operate as the definitive translation layer. They are the exact mechanism by which digital logic exerts physical force onto the world.